lecture 35, and we were discussing flame length last time. And we saw an experimental relation which could be used to get flame lengths for various kinds of fuels. So, the last thing which we looked at yesterday was how long is a propane flame compared to a methane flame, how long is a butane flame compared to a methane flame, stuff like that. So, we understood that part of it. So, we used one expression which is 1300, flame length is 1330 times the volumetric flow rate of fuel multiplied by a temperature ratio divided by log of 1 plus 1 over S. S is the molar ratio, stoichiometric molar ratio of the ambient fluid to the nozzle fluid. So, typically the ambient fluid is air, and typically the nozzle fluid is just fuel, but there can be also fuel with a diluent, and the oxidizer need not be air always, it can be some mixture of oxygen and nitrogen, and so these things can change a little bit, but we understood that the flame length in fact is proportional to the volumetric flow rate of the fuel. So, this much we saw. Now, before we look at some more experimental results, some more trends of the flame length, we saw some trend of the flame length yesterday on the fuel type. So, you change the fuel type, you go from lower hydrocarbon to higher hydrocarbon. We looked at only alkanes yesterday, methane, propane, butane. If you make it a heavier alkane, then we saw how the flame length changed. But we can look at various other possibilities. For example, we can think of mixing some air with the fuel, we can think of mixing some diluent, that is, let us say something like nitrogen, which does not participate in the combustion, with the fuel and see what happens to the flame length. But for the time being, I will just put that on a hold and do a simple analysis of flame length. Okay. And some kind of a simple scaling argument can be used to get an expression for the flame length. So, let us try to do that. So, this will give you an approximate idea of what actually happens in a situation like this. So, we have the flame and we want to think about couple of time scales. One is a convection time scale, which we call a tau convection, and there is also a diffusion time scale pertaining to this problem. Now, the convection time scale will be the time which a packet of fluid here takes to move along the axis and reach the flame tip, starting from here reaching the flame tip. Now, where is the flame tip? This is the burner exit plane, this is the plane which touches the tip of the flame. We call this LF. So, if your velocity here is some, at this location if the velocity is VE, then the convection time is LF by VE. So, a packet of fuel will move to the tip of the flame purely by convection, isn't it? Because this is on the center line. So, it will move purely by convection. It just moves straight to the top, carried by the flow. So, one estimate of this is LF divided by VE. Okay, VE is the burner exit velocity. Mind you, these are expressions which are kind of approximate relations. So, this is some measure, some estimate. This is an estimate of the convection time. Now, we can also have a diffusion time associated with these processes. So, what is the diffusion time? If you think of, let us say again a packet of fluid, but diffusing to the flame in this direction. So, these are both happening. So, we have this packet moving along the center line because of convection and reaching the flame tip, but we also have some packets of fluid moving from the center line to the flame primarily by diffusion. I say primarily by diffusion because the main momentum is actually axial, isn't it? And so, this we can roughly say that this happens primarily by diffusion. So, if you do that, then we can say that the diffusion time is actually some length scale divided by a diffusion velocity of the fuel, some diffusion velocity of the fuel. Okay. Now, what is d? D is actually the diameter of the tube. D is the diameter of the tube. So, if d is the diameter of the tube, d divided by a diffusion velocity of the fuel is a measure of the characteristic diffusion time of the process. If you think about it, you may not like what I have written. You may think that it should be the radius of the flame divided by a diffusion velocity. You might think like that, but notice that the flame can be actually wider at different heights. The flame radius, I mean the one which I marked with this red arrow, can be larger than the tube radius. Okay. And in any case, when we write these terms, we mean kind of like the order of terms. An order is like the maximum value. So, it is okay to say that the flame is the flame width is such that the diffusion time can be characterized by this d divided by a diffusion velocity of the fuel. Okay, because you see from the way I have drawn that it is probably more than the radius of this. Okay. So, diameter is okay. Natural tendency would have been for you to think that okay, it is moving from here to here. So, it should be radius, but then this radius may not be the same as this radius. This radius may be larger even. Okay. Now, this is easier because this is flame length divided by the exit velocity, some velocity which we know, isn't it? When we are trying to get these estimates of these characteristic times, we are interested in writing these times in terms of things which we know. So, this V e is the exit velocity at the burner, and this is something which we know. We do not know the complete distribution of velocity at different places. Mind you, if you go up, you know that even the center line velocity does not remain V. The center line velocity is actually equal to V e only in the potential core. If you go above that potential core, if you keep going higher in the flame, the center line velocity will decay. Remember that the jet expands and the center line velocity decays and it spreads, right. So, this V is just an estimate. Okay. Now, this nevertheless gives you some time for the convection process, some time scale for the convection process. For the diffusion process, we have the diffusion velocity at the denominator, it's small d divided by V diffusion F. So, what is the diffusion velocity? How do we write this? Now, we already know this, we already know something about diffusion velocities. We did this some time back. So, let us try to recollect that. Maybe I will do it on a different page. So, we used to write something like this. We used to write V I as a capital V plus V I minus V. For a one dimensional case, we do not need to write the vector sign, but actually this is a vector sum. Okay. So, what was this again? V I is the absolute velocity of the ith species, isn't it? And what was capital V? Again, this we did long time back, I think before we did the premixed flame derivation. This is the bulk velocity, this is the velocity of the mixture. Okay. This is the velocity of the ith species, this is the velocity of the center of mass of the mixture, and there is a difference. So, this is what I have told you then. I told you then that okay, you have this mixture, but these are different components, each one of them can move at a different velocity, and capital V is kind of a representative average velocity of that mixture. So, the individual species in a mixture, and since we are doing combustion, there are various species involved, it is not one substance, right. So, they do not necessarily move at the speed of the center of mass of the mixture. So, there are differences, and those differences are given by V I minus V, for which we gave a name. We called it a diffusion velocity, correct. So, if you recollect all that, then V I is equal to V plus V diffusion I. This again we had done, correct. And what is the next step? We also multiplied this by rho I, both sides. So, we actually did this. So, this is the mass flux of the ith species. So, this is m dot I double prime, and this is y I times rho v, and this rho v is m dot double prime, and we called the last one m dot diffusion I. So, what is m dot double prime? Anybody remembers that? M dot double prime, it is the mass flux of the mixture, mass flux of the mixture. Okay. So, we said that this is mass flux of the mixture multiplied by yi. So, this gives you the bulk flow contribution to the mass flux of the ith species. So, this is telling us a story. This is telling us that the mass flux of the ith species is equal has two contributions. One contribution due to the bulk flow, the other contribution is due to the diffusion effect. There is a diffusive flux also. So, the mixture has this mass flux, and each individual species gets a contribution to its mass flux because of the overall mixture flow, but it also flows relative to those. Also, it diffuses relative to the center of mass of the mixture. So, there is a mass diffusion component, and we are actually interested now in V diffusion I now today. Why? Because we want this, correct. All right. So, what can we say about this m dot double prime diffusion I, which we had done some time back? We can say something about it, isn't it? This will come from Fick's law. Okay. So, at the simplest approximation, this is dy. Actually, we should write curl del yi del x. Let us say if it is one dimensional. In fact, if it is one dimensional, then it can be d, not delta. And this m dot diffusion I, this is also, you can see from here, that is rho I V diffusion I. Okay. So, this is this. From here we can write this. And this would mean that V diffusion I is actually, from here we can divide by rho I. So, it is minus rho by rho I d dy I dx for the one dimensional case. And what is rho by rho I? It is minus 1 over yi. Okay. Because rho I is the partial density of the ith species, which is the mixture density multiplied by the mass fraction. Correct. So, that is how we get an estimate of the diffusion velocity. And our diffusion here in the problem that we are talking about is radial. It's radial, isn't it? So, for this case, we actually can use a similar expression. So, for the fuel we will write V diffusion F as minus d by y fuel dyi dx. Okay. dr, sorry. Yes, this is so dyf dr. So an estimate for this diffusion velocity is like it should be something like d divided by small d. D is diffusion coefficient, and that r, we are saying it's of the order of d. Why? Same logic as before, isn't it? That if you go at a particular height in the flame, we are saying our characteristic length scale is of the order of small d. So then this term becomes d divided by V diffusion f we wrote as capital D by small d. This one here. This we can write here. So this becomes d squared by capital D. So now what are we going to do? We are going to say that this convection time scale and the diffusion time scale, they are approximately of the same order. They can be equated. They are not exactly the same, but they can be equated. So the time that is taken by a fuel particle, a packet of fuel to reach from here to there is approximately the same time that a fuel particle takes from reach from here to this side. Okay, of the same order. Another way of justifying this is that if you take the energy equation, if you non-dimensionalize this appropriately, then before the diffusion term in the energy equation, the diffusion term of the energy equation will be d2 temperature dr2, that sort of term. Before that term, there will be a coefficient which will be a ratio of the convection time scale divided by the diffusion time scale, and that should be of the order of 1. But we haven't done that non-dimensionalization of basic equations. So for us it is just sufficient to say that these two time scales, the convection time scale and the diffusion time scales, are approximately equal. This is the best estimate that we can do. They are roughly the same. So if we say that these two are roughly same, what is the advantage that we are gaining? We are immediately we'll be able to see how the flame length varies on various things. Okay. So let's do that. Let's equate these two. So let's equate this one with this one. This is the convection time scale, this is the diffusion time scale. If you equate the two, then this LF is like d squared VE by capital D. It's proportional to that. It's better to write this as a proportionality. Okay, so that's what we get from here. And is this correct? Can we say something about this? Do we already know whether this is correct or not?
Can you repeat it again?
Yeah, repeat these two. I mean, why these two are equal? These two are equal because actually I gave two reasons. One reason I didn't really elaborate on. The first reason is that the convection time scale and the diffusion time scales are expected to be of the same order, so that's why you were equating this. That's all. So we are saying that roughly the time taken by this packet to reach there is similar to, not exactly equal, but similar to the time that is taken by this packet to reach there. Okay. So that's the first one. The other logic that I gave is that if you take the energy equation and even the species equations, and if you appropriately non-dimensionalize those, then you will get a ratio of a convective term to a diffusion time scale, convective time scale to a diffusion time scales before the diffusion term in the energy equation or in the species equations. Okay. So this I am saying without actually proving this. And to keep all terms of the same order, the convective time scale to the diffusion time scale ratio should be of the order of 1. Now, even though we have not done it, but you can probably relate to this sort of a discussion if you think about what you may have done in fluid mechanics, because we do order of magnitude analysis and we set terms of we will look at the terms, orders of various terms, and then we sometimes we say that okay, equation has 5 terms and 4 terms are of the order of 1, so the 5th term also has to be of the order of 1. Okay, that sort of argument. So it can come from that sort of argument also. But for our purpose, as of now, it's just sufficient to say that these 2 time scales which are marked here, then they cannot be very different. So they are of the same order. So you can equate them, but actually we are not even equating. We are just saying that they're kind of similar, and then from that we get this. Now, is this something which we can verify somehow? I mean, is this something which we have already seen? Can this be verified? We did some scaling argument, but do you think this is reasonable? What is this telling us?
Like V into D square is a measure of flow rate. So we already seen that it is proportional.
Correct. So this tells us that the flame length is proportional to the volume flow rate of the fuel, isn't it? Because imagine multiplying this by pi by 4. So then it's pi d squared by 4 is the area at the exit of the tube multiplied by the velocity at the exit. So that's the volume flow rate. You can multiply the numerator and the denominator both by pi by 4. So that is legitimate. So that means flame length doesn't really depend on velocity individually, but it's actually dependent on the flow rate or the fuel flow rate. The flame length is proportional to the fuel flow rate, and the flame length is inversely proportional to the diffusion coefficient. So if you think about it, we actually have some justification of this, because definitely in the expressions which we saw yesterday, flame length was proportional to the volume flow rate. Correct. So we saw that. So there is an experimental flame length expression, which is what we wrote yesterday. So it is indeed proportional to QF. So this simple analysis of matching time scales, it just tells you that it's possible to argue out why, in a simple way, it's possible to argue out why the flame length is proportional to the volume flow rate of fuel. Okay. And we know that this is true because this has been experimentally verified. Now, after this, we'll like to go to some more results, but maybe we should also do something else. Maybe we should also talk about S a little bit. We kind of know about S. What is S? Yeah.
We've also seen that LF is directly proportional 1 by D, and the theoretical result.
Yeah, theoretical result. That's correct. Theoretical results tells you that the flame length is proportional to 1 over D, the diffusion coefficient. So even that can be verified. Okay. Now, so this is okay, and we have now some understanding of why flame length is proportional to QF. But let's think about S a little bit more. So S is moles of ambient fluid divided by moles of nozzle fluid, ratio of like this, moles of under stoichiometric situation, isn't it? So that we had done yesterday. But there can be some situations where we are doing a few things differently, and we can for example use primary aeration. If we use primary aeration, then the fuel stream has some air mixed in it. So, it is no longer a situation where when you are sending just the fuel through it. So, is it a premixed combustion situation then? Not necessarily. If you make it within the flammability limit, if you mix the air in such a way that it is within the flammability limit, then it approaches premixed combustion situation. But then you can choose to mix some percentage of theoretical air that is required instead of the full stoichiometric air or more than that stoichiometric air. You can give some small amount of air, and even that air qualifies as primary air. And in that case, the combustion that you get, it is still diffusion combustion, but it's little different, slightly different from the diffusion combustion that you get when you are sending out just pure fuel. Okay. So, the question that we have to think about is that if we are using primary aeration, do we change something in this expression? Because otherwise, if it is the same expression, it is going to give you the same value of flame length. But if we mix some air with the fuel stream, the flame length will not be the same. Anybody can tell you that, right? If you have one situation when through the nozzle you are sending out just propane, then you get some flame length. Okay, just propane coming out from a circular tube to an ambient oxidizer field. So, you get some flame length. Now, if you mix some amount of air with that propane, the flame length will obviously change, because the flame length relates to the fuel's necessity of getting oxidizer and getting burned, right. But if you mix some air with the fuel, then part of the need that the fuel has for its combustion is already met through the primary air, through the air which you are already supplying with the fuel stream. So, that must change the flame length, but if you use the same expression, where will the change happen? There has to be some change in the flame length. Now, this part I think I will ask you to do, not now, but I will ask you to do little later, maybe at home. So, S in case of primary aeration is given by this. So, what is psi primary? It is the percentage primary aeration, and so it is the percentage of the air which will give you combustion, which will give you stoichiometric combustion. So, for certain amount of fuel you need certain amount of air for stoichiometric combustion. So, part of that, a certain fraction of that, certain percentage of that you are supplying as a primary air. So, that psi pri, the notation psi pri which you saw in that expression, is in fact that percentage. Okay. And what is 1 over S pure? So, this S pure is obviously when you are not supplying air, not supplying primary air with the fuel, just the basic S. So, the basic S is now being called S pure, and then based on that we can calculate S. So, if you do that, then what happens to flame length? Let us psi primary, okay, it will be clear now. Psi primary is that percentage of the percentage of air that is required for stoichiometric combustion. So, let us look at this, it will become clear now. All right. So, there is primary aeration. This primary aeration is percentage of stoichiometric. If you look at the x axis, primary aeration is percentage of stoichiometric, fine. So, that means you are giving a certain percentage of the air that you require for stoichiometric combustion. So, that means a number of like 40 here, 40 means 40% of the stoichiometric requirement of air is given as a primary air. So, psi primary becomes 0.4 in that case, because it is 40%. That is the way we do the calculation for S. And this plot actually shows you S also. S is shown with the dashed line. So, this is S, this is the dashed line thing, and S is also read on the right hand side axis. Okay. S is also read on the right hand side axis. So, you choose the primary aeration. Suppose the primary aeration is like 20%, then you reach here and you go this way, you see that S is something like 2.5 or so, and for that case you can also find out what is LF by LF naught. So, LF naught is for the pure fuel. LF naught is for the pure fuel. So, what do we conclude from here? When the primary aeration is 0, then it is the pure fuel coming out. It is just the fuel coming out from the nozzle. Okay, in that case, LF by LF naught is equal to 1, as you can see from here. So, that means as you keep adding air to the fuel stream, the flame length keeps going down. That is reasonable. That should be reasonable, isn't it? Because if you do not supply any air with the fuel, then the flame will tend to be longer so that it can be in closer touch with oxygen, with more oxygen of the air. Whereas if you start giving some amount of air, then the flame length will start reducing. If you give closer and closer to stoichiometric amounts, then the flame length will actually start keep getting lower and lower. But he also marks this rich limit. That means for this situation, it's like it's going towards it's reaching the flammability limit basically. So it's going towards premixed combustion in that case. Rich in fuel, because you're giving less than stoichiometric amount of primary air. So the mixture that you are sending through the nozzle, is now within the rich flammability limit. If you cross over to this side,
below this it will not burn.
Below this, it's not. From a premixed combustion point of view, it's not flammable.
As we are increasing there, means we are increasing the air, right?
Yeah.
Air composition.
Huh.
So which limit?
Okay, so your confusion is that if you are increasing air, then it should become more lean, but it's not that. See, if you have this much amount of air, then this amount of air is so small, then it is not even within the rich flammability limit. The mixture has a lean flammability limit and the rich flammability limit, isn't it? So if you give very little air, that mixture is still a rich mixture, but not within the flammability limit.
It will not be flammable if you don't have
It's not.
oxygen in the atmosphere.
Yeah, so suppose you give 5% primary air. Then you are about here, then it is still a mixture, but it is not within the flammability range. Okay, I am not talking about that outside air anymore. I am talking about just the fuel air mixture which is coming out from the nozzle. So with 5% primary aeration, it is nothing. It is not within the flammability limit. But as you increase air, the mixture is reaching a stage where it can actually burn as a premixed flame. Okay, so that is that rich limit.
This means that after the 60% it becomes a premixed.
Yeah.
And if it goes to 100%, then it will become a stoichiometric.
Yeah. then it will act like a Bunsen flame. Anyway, so this tells you something useful. It tells you that in a practical situation, when you want to heat something, let us say, and when you want to have some control over the combustion process, if you mix air with the fuel stream, you can change the flame length. Suppose you are not happy with the flame length. Suppose you want to make it shorter, then you add more air. Or you think that the flame length is too short, then you reduce the amount of air. Then the flame length will become larger. So, this has practical applications. This has practical implication. So, this is one situation. What I told you a few minutes back is that based on what I told you about the definition of S, and remember we in fact calculated S pure yesterday, isn't it? We wrote this at x plus y by 4 divided by something. What was that? Chi O2. That is the mole fraction of oxygen in the oxidizer. So, we did that. This was a simple thing to do. Fine. Now, you have been told what is psi prime. So, can you derive this for this situation? Not difficult, but please do this yourself. So, I am asking you to verify at home. Just a few, 1 or 2 or 3 lines of derivation.
One, the example of this kind of control is like in welding. Welding also we use this air.
Yeah, so flame length control is actually important, and we had seen some example of this previously. Remember, we had actually looked at the stability diagram. Okay, these lines and this, that also had primary aeration in it, isn't it? So, there I told you that it is not actually fully premixed situation. Remember, there is a flashback zone, looked like this. So, it is often used in practical situations. Practical burners use some amount of primary air, and then the rest of the air picks up from the surroundings. So, that is secondary air. So, it helps you to control flame length, it helps you to control the regime which you are in, make sure that you are in the stable operation regime. Right. So, this is one situation, and there is another situation for which also I want you to put in some effort. That is, I told you about primary aeration, but if you think about the oxygen content in the oxidizing stream, you can think about this also as to whether this makes sense. So, this is now the effect of oxygen content on the oxidizing stream. Suppose you do not have exactly air, you have less than 21% oxygen or maybe more than 21% oxygen, then what will happen to that flame length? You can again get this from the same formula for experimental flame length, but think about how you will use it. And if you are able to do that, then you can make a plot like this. So, in this plot, the relative flame length has been plotted. Flame length divided by flame length for 21% oxygen. 21% oxygen is baseline. Of course, 21% oxygen is baseline because we are actually, in case of 21% oxygen, talking about air. So, that is a good reference, because you can think in terms of how is the length of the flame compared to, how much is the length of the flame compared to the situation when the compared to the situation when you have air as the oxidizer. So, different cases, sometimes you do not have air, sometimes you have air, always it is better to compare with the flame length which you get when you have air. So, if you have 21% oxygen, then on the y axis you will read 1, LF by LF 21% will be 1 obviously. Now, if you have less than 21% oxygen, what happens? The flame is longer. Is that understandable? Okay, that is understandable. So, here we are talking about only a fuel coming out. We are not talking about mixing oxygen or air with the fuel, but we are talking about the surrounding atmosphere. That atmosphere, in one case it is air, in all other cases it is oxygen plus nitrogen. Oxygen may be less than 21%, oxygen may be more than 21%. Okay. So, if it is less than 21%, you get a long flame, and if it is more than 21%, then the flame length actually starts coming down. In fact, we have been doing several experiments in the lab, and maybe we can take a look at some of the photographs that we have taken when you have more than 21% oxygen. So, that is called oxygen enhanced air, and we see that the flame length comes down. So, this is another situation. Again, this is for circular port. Let us remember that whatever results I have shown you so far is only for circular port, just to make sure that the discussion is shorter, because I do not want to go into other kinds of burners and slot burner and other kinds of burners. So, circular port methane, this is the flame length situation. And there is another case when we have more than, we can also have situation when we have fuel dilution. That is also very much possible. In case of fuel dilution, we have a mole fraction a chi DIL, DIL for dilution. So, there can be a chi diluent in the fuel stream. So, let us say you have methane, you have added some nitrogen to it, and there is like 20% nitrogen in methane. So, chi diluent will be 0.2. So, it is a mixture of methane and nitrogen. Mole fraction of methane is 0.8, mole fraction of nitrogen is 0.2. So, you can have a situation like this. So, in a situation like that, S will be given by x plus y by 4 chi O2, and I would like you to verify this also. So, this also needs to be verified. I think I had a plot of this also, but somehow not been able to locate it now. Yeah, but you can see a plot from the book, and you can also generate yourself. So, this is specify chi diluent, calculate the value of S, and then once you have the value of S, from that you calculate the length of the flame. Okay. So, what does this tell you? If you have no chi diluent, okay, chi diluent equal to 0, if you have that, if then S equal to the usual thing, the usual S, then the same flame length as the usual case. But if you have chi diluent, then what will happen to S and what has happened to flame length? So, S will decrease, and if S decreases, what happens to flame length from the relation that we know? This is the relation. S is decreasing, right? So, the denominator will increase. So, flame length decreases because now we are not sending that much amount of fuel, sending less amount of fuel. Okay. So, in the next few minutes, I want to talk about one example problem which is given in Turns's book. We may not be able to do it fully, but nevertheless discuss it to some extent. Actually, I do not intend to do it fully also. This is example 9.4 of Turns. And I want to discuss this just to give you a flavor of how practical calculations can be done with what we already know. So, this example, I do not have the problem statement here, but I will roughly tell you what it is. It talks about making a natural gas burner. Okay. So, the burner that you have at home, there is a burner block in which there are multiple small holes, right, large number of holes, and these like for example, what we have for this LPG burner at home is something like this. There are multiple number of holes and the fuel air mixture comes out from this. In fact, it will be good if you can dismantle a burner and see exactly how the fuel and air are mixed. You can take a look at that, but mixing is done prior to it reaches the burner. So, it's somewhere here upstream there is a mixing of air with the fuel. So, the fuel air mixture comes out from this through all these individual holes. Okay. But this is the example 9.4 talks about a burner in which it is not exactly premix, but there is some primary aeration as we have been talking about. So, there is he is talking about making a natural gas burner. So, it is not LPG like what we have at home, it is a natural gas burner and we will take natural gas to be methane. Okay. We have a natural gas burner and we will take it to be methane, and it has a diameter of basically 160 mm, and on that 160 mm circular thing you have to place multiple holes and it has to deliver 2.2 kilowatt at full load, 2.2 kilowatt at full load, and it should operate at 40% primary aeration. The problem statement is there, so I do not think you need to write down, but maybe you can just write down these numbers. And it is also mentioned that for stable operations, the port loading. Now, what is a port? It is all of these individual holes. Okay. So, a port is one individual hole. The port loading should not be more than, for stable operation, port loading should not be more than 10 watt per millimeter squared of port area. Millimeter is a good unit for port. I mean, for a port you will not use meters, right, not even centimeters. So, it is what do you expect the port diameter to be, like few, yeah, small, 2-3 mm, things like that. So, it's 10 watt per millimeter squared is the limit on the port loading, and the full load flame height, the full load means that 2.2 kilowatt when it is able to deliver the 2.2 kilowatt, the full load flame height should not be, that means flame length should not be actually more than 20 mm. So, how do you solve this problem? There are some constraints given, and you have not been told what is the number of ports that you have and what is the diameter of the ports, and that is a problem. I mean, that is what you have to solve for. Okay. So, you have been told that you have to generate this 2.2 kilowatt and subject to some constraints, constraint like flame length should not be more than this, the port loading should not be more than this, things like that. But you have not been told how many ports you need to have and what should be the diameter of each port. So, that is what you have to calculate. So, that is kind of a design thing that we are doing. And we will not be able to do it fully today, but let us start at least. So, first we will try to use the given information and see whether we can say something about the number of ports and the diameter of the port. We have to start from there. So, our approach will be that we decide on the number of ports and the diameter of a port, then see whether that satisfies the flame length and power and things like that. Okay. So, how do we do it? We have a total area which we are giving through the ports as n times pi d squared by 4. So, d is the port diameter, n is the number of ports, and the constraint that we have is like m dot f delta h c divided by a total, sorry this is h c, delta h c. So, this is 2200 watt divided by a total should be 10 watt per millimeter square. 2.2 kilowatt it is giving, and that 2.2 kilowatt has to get distributed over a total area. Total area is the sum of the areas of the ports. So, the 2.2 kilowatt divided by total area must be 10 watt per millimeter square. So, in the limiting case, when it is able to give 2.2 kilowatt, it cannot cross 10 watt per millimeter square. So, if you cross that, what will happen? Why does the problem state that for stable operation port loading should not be 10 watt per millimeter square, should not be more than 10 watt per millimeter square? And what does stability got to do with the 10 watt per millimeter square value, like the port loading? If you send too much flow, that means if you try to make from 10, if you try to make 15, then you have to send more fuel and then consequently more air also with it. You are using some primary air with it, and that can result in some lift off, some blow off, things like that. So, to remain within the stability regime, you are controlling the loading at the port and keeping it at 10 watt per millimeter square. Okay. So, if you do this, then from this calculation, say mind you A total is n pi d squared by 4. So, this will tell you that n d squared is 280 millimeter square, fine.
So, is there any factor from the quenching point of view for a safe?
Yeah, one should actually check that also, but most likely we will be okay. So, let us see. So, that is a good question actually. The question was, is there something in this design which deals with stability? Okay. So, the good thing here is that the mixture that we are sending is not exactly flammable possibly, isn't it, because you are not giving full amount of air, you are giving only 40% of primary air. So, you do not really have a mixture which can actually turn back inside this. So, that is one point. But the other point is also that if you choose the number of ports properly, if you choose the diameter properly, keep it small, in any case it will probably be satisfied. So, what Turns does is somewhat arbitrarily he chooses. So, he chooses n equal to 36, which gives us d equal to 2.79 mm. So, he chooses 36. How he chooses 36 I do not know, but it can be the other way, that you choose a small enough diameter and then you choose the number 36. I think that is a good better way probably to do it, and 2.79 is okay, because for methane what was the quenching distance like? It was not like 0.5 mm or something, no, bigger than that. It was, what was the quenching distance, for which fuel the quenching distance was the lowest? Hydrogen. So, this is not hydrogen, this is methane, this is much better. Plus you are not supplying the full layer. So, to me it looks like 2.79 is fine. I do not remember the value of the quenching distance of methane, but it is more like 2 mm or so. Okay. So, 2.79 is fine. So, you got n equal to 36. It could have been something else, but this is the design process. So, we are starting with something. We start with this, somewhat arbitrarily we choose something. That is what people do in design. You choose something and then see whether it works out or not. So, what is our next job? Our next job will be to actually try and see whether this satisfies other conditions which require to be met. That means, if you in fact calculate the flame length based on what you have, okay, when will you have the largest flame length? When it is like full load 2.2 kilowatt, 10 watt per millimeter square, then you will have a flame length. See, if that flame length is less than what is specified, it should be less than 20 mm. I mean, maximum it is 20 mm flame length, not greater than 20 mm. So, if n equal to 36, d equal to 2.8 mm, if this gives you a flame length of 20 mm or so or less, then you are fine. So, that is the check that we have to do, and I think we are running out of time. So, we will do that in the next class. All right. Thank you.